Hello, everyone. Welcome to the August 8th edition of the Blazor Community Stand-Up. Today, we have a very special guest, Katelyn Gadd, and she's going to be presenting the .NET WebAssembly Jiterpreter.
Hi, everybody. I work on the .NET runtime team, mostly on our WebAssembly runtime, so things like JavaScript interop and the JIT and AOT compilers.
Thanks. And I'm Mackinnon. I'm a developer on the Blazor team. So before we jump into the presentation, we're going to go over some community links, which is something that we do every Blazor community stand-up, where we go over some of the things that the community has been up to, whether it be community projects or blog posts or videos. So I'll go ahead and share my screen and we'll get that going. So the link to this URL list, by the way, is in the description of wherever you're watching this stream. So first we have a Blazor component library called ant-design Blazor. And this is based on the React library called ant-design, but it's just a Blazor reimplementation. And so we might have lost Kate. I'm not sure. But anyways, I'll just keep going and hopefully she rejoins. But yeah, so this is a, oh, she's back. Cool. So yeah, it's a very full-featured component library. It has just a ton of various components that are like some are very niche, but they would be very useful for certain types of applications, like mentions, for example. It's just a very specific feature, but so useful for like if your app calls for that type of feature. And yeah, just tons of different components to choose from. The styling's very nice, so it's another component library to keep in mind when you're deciding which one to use for your Blazor app. Next, we have XAML for Blazor. And this is actually a feature request that we've had a few times on the ASP.NET Core repo, the GitHub repo. But it's not something that the Blazor team itself is planning to implement. So it's cool to see a community project that supports writing Blazor components using XAML. It's distributed as a NuGet package, so it's pretty easy to set up. So if you're coming from a background like WPF or UWP, and you want to stick to the same kind of programming model, you can use that with Blazor now using this library. So I haven't personally tried it, but it looks really interesting and it looks very easy to set up. You just have to render this XAML for Blazor component and pass in the type of your XAML control, and it just renders directly in your app. So very cool. I'd be curious to see what people think about it. All right, next we have a blog post by John Hilton, and this is going over some of the new changes in .NET 8 with Blazor, in particular server-side rendering. So this kind of goes over how to set up the project, create a project from the project template. It walks over how the project is set up, how it runs, and it also talks a little bit about enhanced navigation. So one really cool feature we have in server-side rendered Blazor is when you click on links within your app, rather than doing a full page refresh, it actually intercepts the navigation or intercepts the request of the server and merges the response to HTML with the existing HTML on the page. So you don't see any flickering, any user entered state stays there. So it feels kind of like a single page application, even though it isn't. So yeah, this blog touches on that a little bit as well. Just a pretty good like general overview of some of the features that are coming. And then the same person actually has another blog post that talks about some of the more advanced features like form submissions and adding islands of interactivity from within your app. So if that's something that you want kind of a nice overview of, then check out those two blog posts. Next, we have a YouTube video by Daniel Hendricks, and this is called How Blazor Saved My Day. I ran across this video and I thought it was a very compelling example of having a .NET MAUI app and then finding a Blazor component that you think is useful and then just pulling it in as a Blazor hybrid component. In this case, he was building an app that warranted a calendar component, and he found one that was implemented in Blazor, even though he hadn't been using Blazor in his app yet. It was just a normal .NET MAUI app. But with just a few simple steps, he was able to pull in the component and add it to his app and have it feel still like a native app. So I thought it was really interesting. Definitely check that out if that's something that you want to do in your own app. Next, we have a live stream that's upcoming on the Blazor train, and this is an overview of a lot of what's coming new in Blazor and .NET 8, which I'm guessing will be a lot of the server-side rendering features. I'll be really interested to see how he presents this. So if you're kind of new to this new Blazor approach of server-side rendering, or you want an update or just a general overview, I think this will be a cool stream to check out. So that about wraps it up for the community links. I think we will hand it off to Katelyn for the main part of the show.
There we go. All right.
Okay. Yep.
So as mentioned before, I'm going to give a technical overview of the Jiterpreter. So the Jiterpreter is a just-in-time compiler that's integrated into the Mono interpreter, which is what's used by the WebAssembly version of the .NET runtime. This is what powers Blazor, it powers Uno, and various other technologies. And if you're unfamiliar, a just-in-time compiler is distinct from other types of compilers in that it will compile your application on demand, potentially one class or one method at a time. And the Jiterpreter is a tracing JIT compiler, which means that instead of compiling entire methods or classes, it compiles short traces that replace small sequences of interpreter opcodes. This occurs on demand for the code that is hottest while your application is running. This addresses multiple limitations that we hit with the WebAssembly platform, and it gives you much better performance for scenarios where it's not possible to ahead of time compile your entire application. So as I mentioned, most JITs operate on methods or classes. Why are we not using the whole method JIT that is in Mono or the whole method JIT that's in Core CLR? And why are we not using a whole application AOT compiler like also is available in Mono and Core CLR? So one reason not to use an AOT compiler is that it increases your build and download time considerably. And in some cases, it could even make it impossible for the application to start. And the reason we're not using a whole method JIT is that WebAssembly does not provide an equivalent to executable memory like is available on most platforms. And there's no standard API for JITting code either. There is something unique to web browsers that allows us to compile some WebAssembly on the fly, and that's what we're using. But it limits the size of the code you can compile to 4 kilobytes, and this is too small for most methods. So instead, we take the interpreter opcodes that are generated at runtime by the Mono interpreter. It takes the CIL from your DLL files, and before a method ever runs, it turns all of that CIL into its own set of opcodes. And after this code generation is finished, the local variables in your method have become fixed memory offsets inside of a little stack. And some complex operations have turned into simpler operations. So loading or storing a local variable becomes just a raw memory move. Null checks may disappear or be inserted in specific places. And more importantly, things like generics disappear. If you're performing a generic operation in your CIL inside that DLL file where you to decompile it, you'd see generics. At the point where the interpreter is done generating code, that's all gone. It's operating on ints or floats directly, which improves the performance a lot and furthermore allows optimizations that the interpreter performs, like eliminating dead code, devirtualization, and inlining to get you the best possible performance considering that we're using an interpreter. And the Jiterpreter inserts itself into this process. It inserts something called a prepare point into that stream of interpreter opcodes at key locations like the entry point of a method and branch targets. These prepare points are special opcodes that when we execute them, they bump a little hit counter that's tracking how often we've hit this point. And once that counter reaches a set threshold, we decide, okay, it's worth it to try and JIT compile a trace starting at this location. And if we're successful, we turn that prepare point into something called a monitor point. And at this point, we have this JIT code. And what we're going to do is every time we execute it, we're going to monitor its behavior. We're going to figure out whether this JIT code is behaving well. I'll explain more later about how that works. Once we've monitored our compiled code for a while, we finally turn that location into something called an entry point. And an entry point is effectively just a little function pointer, pointer to compiled code. And now when the interpreter hits that entry point, all it needs to do is call a function and then resume executing the rest of your method. And you can just see a simple flowchart here showing how we create a prepare point. It will either turn into a no op if it fails to compile, or into a monitor point. And then once we're done monitoring the compiled code, it will either turn into a no op again because we rejected it, or it will turn into an entry point, at which point your JIT code is all done and ready to go, and it will just replace large sections of the interpreted code. So there are extensive limitations on what we can actually JIT compile into a trace, especially given the limitations like the 4 kilobyte size limit. One good example is a conditional branch might target a location outside of the trace. We're only compiling a small section of your method. Your method might have 1,000 statements in it. It's not possible to fit all of those into a 4 kilobyte little blob. So if the target of the branch is outside of the trace, we have to hand that off to the interpreter. We have to leave the trace and hand off control to the interpreter. Similarly, if you're going to call another method, that would require creating a new stack frame. We'd have to pass arguments around. So likewise, we hand that off to the interpreter. We exit the trace. When we encounter these scenarios where you can't compile the opcode, we generate something called a bailout instead. A bailout essentially is a little return statement inside the trace. And what it does is it returns a displacement value to the interpreter. That tells the interpreter exactly where to resume execution so that a trace can exit 2 opcodes in or 100 opcodes in and everything will work correctly. And execution resumes at the point where failure happened, which means that we can also use this for exception handling. A trace that needs to throw an exception, instead of having to actually throw the exception itself, it just bails out and it tells the interpreter, hey, this opcode that failed, I want you to run that opcode again. And the interpreter will fail to perform the opcode, and then it will finally throw that exception we wanted to throw, which is another way that we are able to kind of offload that work to the interpreter. Which gets to that monitoring phase I mentioned before. Bailouts can occur inside of control flow. You might have an if statement that's taken 75% of the time, and then there's a throw inside that if statement. The result is that the bailout for that exception would be conditional. We don't know in advance whether or not that's going to be hit. I said it might be 75% of the time, but you might have a method where it throws 1% of the time. The performance of those two methods is going to be very different. We can't tell the difference between those at compile time. So the monitoring phase is our solution for this. Every time we run the trace during monitoring, we track approximately how many opcodes it was able to run before it bailed out, which gives us an estimate of how much useful work the trace is doing before it terminates. If a trace frequently bails out early, like only a couple of opcodes in, we discard it because there's overhead built into calling that function pointer to enter the trace and then cleaning up after we exit it. We do this monitoring approximately. So we just kind of look at where in this trace did we bail out, because the alternative would be we'd have to actually count how many opcodes we're executing every time we step through, and that would make traces much slower. So we're using an approximation here and just going, oh, hey, it's near the entrance of the trace. This is probably bad, versus it's near the end. So now that I've described how the Sol lifecycle works, we start by compiling traces at hot locations. We monitor them to make sure that they're working well. And then we finally just turn them into a little function pointer that the interpreter can call. I'll explain how the compiler itself actually works. The Jiterpreter itself is a simple single pass compiler. We made a single pass compiler because we wanted to make sure it was fast and it didn't use a lot of memory. It works by translating each interpreter opcode it sees into a group of WebAssembly opcodes. So WebAssembly has its own instruction set, much like any real CPU would. And it just continues translating those opcodes until, for some reason, it can't continue. Those bailouts I mentioned would be one reason it might stop. Another reason would be the 4 kilobyte size limit I mentioned. Once you've translated enough code, you're going to run out of space and you'd stop. At the end of this translation process, if it's successfully compiled enough opcodes, it will go, okay, I've got a good chunk of code here. I'm going to compile it. I'm going to compile this WebAssembly set of opcodes into something called a WebAssembly module, which is basically like a little tiny application. And then we take the trace out of that little compiled WebAssembly application, and we turn it into a function pointer by inserting it into something called the function table. I'll explain what that is later. And while we're going, we have to actually estimate how big all of the stuff we're generating is going to be to make sure we stay under that 4 kilobyte limit. So we need to estimate how big things like function names and local variables and imports and exports all are to make sure we stay under that limit. So that process of translating opcodes is effectively a big switch statement. And the contents of that switch statement are all implemented in TypeScript. And that TypeScript is inspired directly by the interpreter, which is implemented in C. So for every opcode that we want to implement, we look at the interpreter's C, which you can see is kind of a little tiny screenshot here on the top left of the slide. So in this specific case, you can see that this is an opcode to fetch the length of a string. The first thing it does is it loads a local variable at the displacement at 2, which contains an object. Then it's going to check to make sure that object isn't null, which will throw a null reference exception if you're trying to get the length of a null string. And then finally, it's going to pull the length out of that string object and store it into a local variable at the displacement 1. So there's 4 individual operations inside this little interpreter switch statement. As a result, if we want to generate WebAssembly from this, we have TypeScript that generates the equivalent of each of these individual operations as it goes. So for that local variable load here and the null check, we have a little helper called append ldloc cknull, which generates all of the necessary code to do the work of those 2 operations. It will load the local variable, check to make sure it's null, rather check to make sure it's not null. And if it's null, it will bail out. That little mechanism I described before, it will essentially say, oh, this operation failed. I'm going to return control to the interpreter. Then after that, it's going to load the length of the string directly out of the object. You may have noticed that we called a function to get the string length in C. We don't need to do that here because we're generating native WebAssembly. We can locate the offset of the string length member, and we can load that directly. This is a good example of how we're able to actually inline constants. We can inline type pointers and things like that, all directly into the WebAssembly to make it faster. And then finally, at the end of this generated code, we're storing the result into a different local variable.
Just a quick question about that.
Sure, go ahead.
Oh, yeah. Could you touch on why TypeScript was used to generate the WebAssembly rather than something like C?
Great. That's, so there are a few reasons. One of them is that if you want to compile WebAssembly right now, you have to use browser APIs to do it. So we would, no matter what, have a small chunk of TypeScript to implement this JIT. The ultimate answer to this is that it was much easier to prototype this in TypeScript than it was in C, especially because we want to make sure that this isn't going to crash. This isn't going to cause memory corruption issues. So the type safety benefits of TypeScript were really, really valuable here. Were we to choose something else, it might actually be C# instead of C to maintain all of those benefits. We are still kind of on an ongoing basis evaluating whether we should do more of this in C, so it's possible that will change in .NET 9.
Cool, makes sense.
So some opcodes have very complex behavior. The same is true for CIL opcodes. There are some opcodes that will do things like a type check or call a method. For those complex opcodes, if we implement them, we have potentially 100 lines of TypeScript or more responsible for implementing all of that logic via generated code. You can see a very big blob of code on the right side of the slide. You don't need to read it. This is mostly just to illustrate that there are chunks of this switch statement that are very big. If they're not performance critical, what we do for these cases is we just call a helper function that's implemented in C. This little screenshot on the bottom left is an example of one of those opcodes. We load the relevant information, we load the arguments, and we just call a function to do the work, and we move on. That allows us to maintain support for all of the opcodes that we care about without potentially making one trace run out of space by putting an entire kilobyte worth of code in it, and we don't have to take the risk of introducing really nasty bugs into the Jiterpreter by re-implementing all of this. We can just use the existing C inside the runtime to do things like boxing or type checks or very obscure like math operations. And a significant portion of the opcodes are actually very simple. We don't write code for them at all. We instead have tables like the one shown on the right that map a given operation like an add or an overflowing multiply to a WebAssembly opcode that has the exact same semantics. The WebAssembly specification tells you what most of its opcodes will do in very exacting detail. So we're able to go, oh, hey, this CIL opcode for multiply turns into this interpreter opcode for multiply. And we know that WebAssembly will do the exact same thing if we multiply two integers. So we didn't even have to write any code for that. We just filled out this table once, and all of these opcodes work. So a big portion of the kind of difficulty of building this compiler and the complexity in its implementation is control flow. Control flow is what kind of sits underneath things like if statements, gotos, loops, and exception handling. All of that is implemented in terms of control flow. And control flow in WebAssembly has to be structured in a very specific way. This structuring means that we can't do arbitrary goto statements to arbitrary targets. If you're branching forwards, so if you've got a goto statement and then there's a label further down the method, we can translate that directly. Those forward branches require you, however, to begin a block, much like a block in C# with curly braces. You have to begin a block before the source of the branch, before that goto, and the block has to end right before the target of the branch. I'll show a diagram of this later on. Backward branches can also be translated in some cases, but we have to wrap the target of the branch, so the label being gotoed, and all of the sources. So every goto statement that targets the label, all of those have to be wrapped within one special block called a loop block. And furthermore, those branch targets are not encoded and handed to the runtime as labels. We don't say go to label 5. Instead, we encode them as depth. So we say, okay, I'm nested inside 5 blocks. I don't even know necessarily what blocks those are. I want to jump to the third block. So in WebAssembly, that also means that because we're jumping to the third block that we're inside of instead of to a specific label, whether we jump forward or backward depends on what that block is. I mentioned that there are loop blocks. There are regular blocks and loop blocks. If you target a loop block, it will do something different from when you target a normal block. As a result, we have to begin this trace by creating a bunch of blocks. We create a block for every branch target that we know we have. And then every backward branch target, like for a loop, we have to create a loop block. And because I mentioned that the compiler runs in a single pass, we don't know in advance before we compile this trace what branch targets we have. We run into them as we go. And there may be cases where the flow control inside of your function may require an impossible nesting of loops and blocks. This is referred to as kind of unstructured control flow. WebAssembly requires well-structured control flow, which means if you do really fancy things with gotos or loops, we can't translate that directly into WebAssembly. And then, as I mentioned before, some of these branches, some of this control flow may actually leave the trace. So we need to make sure we generate a bailout when that happens. The final outcome of all this complexity is that if we have arbitrary control flow, we actually end up with a little dispatch table, and we have to generate that in a second pass. The illustration I mentioned showing you, this is a sample little bit of WebAssembly that has control flow in it. So you'll see that there are 3 nested blocks. The first one is a loop block, and then the second and third are regular blocks. And then there are 2 branch operations in here. You can see the branch is just a number, basically how many blocks you want to jump out of. And if you look at the arrows I've illustrated here, the branch can go forwards or backwards depending on which block you're skipping out of. So generating this code correctly requires tracking a lot of state and understanding exactly sort of where you are at any given moment to know what's going to happen when you branch out and know how far you want to branch out. So as I mentioned, the compiler itself operates in a single pass, but all this control flow requires a second pass. We introduced a second pass that's kind of referred to as the CFG. It's not a control flow graph, but it stores all that information on the control flow inside of a trace. During that first pass, as we go, we split the trace that we're generating into segments. Anytime we hit control flow, we split it into multiple pieces. And to detect those branch targets I mentioned, for backward branches, the interpreter actually is responsible for recording all of the backward branch targets it encounters while it's generating code, and we keep that little list around. Most traces don't have very many of those, so that list isn't too big. For forward branch targets, your go-tos and your if statements, as we go through that first pass, we build a list and we track that. And then once we've split the trace into all of the segments, we insert little markers for branches and branch targets. So your if statement produces a marker, your else statement produces a marker, your loop will produce a marker at the top and bottom of the loop, and so on. The second pass is responsible for generating the right WebAssembly code at all of those markers to stitch the whole trace together. And the way that will work is if we see a backward branch anywhere, the whole trace becomes wrapped in a loop. And that loop begins with a dispatch table, and then that dispatch table has go-tos in it that will jump to the right part of your code. If you've ever looked at the code that Roslyn generates for enumerator functions or for tasks, the little move next method that it generates, this is identical to that. There's a little state variable that identifies where we want to go next. This dispatch table adds overhead to traces. It makes backward branches much more expensive, but it's still way better than leaving a trace and going back into the interpreter. This is generated in the second pass, as I mentioned. It's not generated in the first pass. So this means that as the first pass goes, it needs to estimate how big all of this generated code will be to make sure that we stay under that 4 kilobyte limit. So here's a kind of simple illustration of the segments in generated code. I think you had a question, so go ahead.
Yeah, sorry, I didn't mean to interrupt, but we have some questions relating to the last couple slides. So one of them is, it sounds like WebAssembly puts quite a few constraints on what is possible and allowed. Is that because it is a low trust environment, and how hard is it for you to work with and around those limitations?
Yes, it's because it's a low trust environment, and that extends beyond. It's not just that they won't let you do unsafe things, but they also don't trust you to generate good code. So the structured control flow constraint isn't something that's necessary for your code to be safe. However, unstructured control flow can make your compiler very, very slow or make it use a lot of memory. This was actually influenced by problems that were encountered with the implementation of Java runtimes, is that unstructured control flow could make the compiler crash. So to keep everything simple, they require a structured control flow for that reason. They want to make the compiler fast and safe and make your code safe. So there are a lot of constraints like that where they disallow doing things that might be slow or might cause a compiler to crash or run out of memory, in addition to all of the constraints that are just there for memory safety, like type checks and whatnot.
Thanks. Yeah, that makes a lot of sense. Yeah, we have one more question. Does this mean that any libc reference in our DLLs will also have to adhere to these caveats?
Yes. If you're compiling a library that's written in C or C# and it contains unstructured control flow, the compiler underneath the hood will do something like this to make sure your code will run. In most cases, it's not necessary for a compiler like, say, Clang to generate this table like I'm describing. We have to do it more often because we're trying to be as fast as possible. But it still will happen. If you were to use something like Godbolt or Compiler Playground to compile some code to WASM, you may find a table like this in it when you look at what's actually generated.
Yeah, thanks. And we actually just had one more pop up. What block types do switch statements and expressions convert to?
Expressions don't use blocks in most cases. The only exceptions to that would be we might have a block if we need to potentially conditionally bail out. So if an expression has to check for null first, we'll wrap the expression in a little block so that we can skip over the contents of the expression if it's null. That's basically the only case where an expression would do it. But then things like switch statements and if statements typically will generate the equivalent of a bunch of individual if statements. WebAssembly does have a way to kind of write out an if statement if you want to, which we do actually take advantage of for things like if statements where possible. That's actually illustrated here. So I mentioned before that traces are split into segments. So in this illustration, we have 2 opcodes. These 2 opcodes have generated 2 segments that are referred to as blobs on the right side of the screen. And then we have a branch target marker, which I mentioned before, and a branch marker. So the branch target marker is generated because we found an if statement that is targeting that location. It's like the equivalent of a go-to. And then we generate the branch marker at the location of that go-to. The goto is a conditional branch. It's a BR true. So if the value is true, we will take the branch. If it's false, we won't. And then what we generate for that is the conditional branch operation itself generates a little WebAssembly if statement. And then if the if is taken, we set that little switch statement selector I mentioned before, the dispatcher value. We set it to, say, 6, which tells the dispatcher where to go. And then we would jump to the dispatcher to restart execution of the trace, which will then take us to the correct location, which in this case is the subtract operation. And then you can see the subtract operation itself is much simpler. We're loading a local variable, we're modifying it by subtracting 1 from it, and then we're storing it back to its original location to modify it. So if you had a loop that was decrementing I until it was 0, you would have this. You would have a subtract by 1, and then you would have a branch if true that jumps back to the top of the loop. So that is the conclusion of the part talking about the trace compiler. There's some related stuff I'm going to go over now. But if there are any questions people have right now about the trace compiler, I can hit on them, or we can cover them at the end in a Q&A.
Yeah, I think we did have a few other questions. They were more general, I think, though. I guess we can answer
those. If they're general,
but...
we'll hit this really quickly, and then we'll circle back to all the questions, because I'm guessing a couple more may come up during this.
Yep, okay, sounds good.
So in an ideal world, as we mentioned earlier on, your whole application would be AOT compiled. And that is possible with Blazor WebAssembly. However, while most of an application will be AOT compiled, there may be things like runtime instantiation of generics or even generation of new code. JSON serialization is a great example of this. The JSON serializer may need to generate new code to handle serializing your data types on the fly. This uncertainty means that in your AOT compiled application, some method calls have to go through a dispatcher. Delegates, for example, don't know whether their target is in the interpreter or in native code. We may have an application where 99% of it was AOT compiled and 1% of it needs to run in the interpreter. As a result, we have this dispatcher that looks at the target and goes, oh, I have AOT compiled code for this. I can call it. I don't have AOT compiled code for this. I need to enter the interpreter. The interpreter, likewise, needs a dispatcher to figure out whether, hey, I'm calling method X. Is this method AOT compiled? Like, am I running inside of an AOT application? If so, it calls the AOT code. If not, it calls through the interpreter and interprets. So there is a little dispatcher that the interpreter likewise relies on that will handle invoking arbitrary code. These transitions are done via little helpers that we call do JIT call and interp entry for each direction. So interpreter to native is a do JIT call, assuming that the code has been JIT or AOT compiled. And moving from native code into the interpreter is an interpreter entry. These helpers, for safety and simplicity reasons, pass everything by reference. So the equivalent of if you made your arguments ref instead of passing things by value, that's used for all of these transitions. And there may be a switch statement inside of these helpers to look at like, oh, how many arguments are there? Okay, I'm calling a method with 5 arguments, so I've got a switch case for 5. I'm going to pull 5 values off of the heap now because they were passed by reference and finally pass them to the destination. However, the Jiterpreter now has a little just-in-time compiler for WebAssembly, which means that we can compile on the fly implementations of these little helpers that implement the transition from one location to the other. We can do this by value, like if you were calling native code, and we know exactly how the stack is laid out. We know the exact signature of the method. So we don't need that switch statement. We don't need to pass things by reference. We can do it all directly. And similarly, we can do some of the same tricks that we do with traces. For transitions from the interpreter to native code, any transition that doesn't actually happen will never be seen by the Jiterpreter, so we don't have to do any extra work for that. If you've got a bunch of native code calls that don't happen, like it's for an about window and the user never opens it, or it's for some special part of your application, we don't see it, so it doesn't cause any problems. For transitions from native code to the interpreter, as it happens, we designed our AOT compiler so that at startup, every possible function pointer that the native code might need, it requests it at startup. So the Jiterpreter is able to maintain a table of every known transition from native code to the interpreter or from the interpreter to native code. This means we're not wasting energy compiling code for every possible call that you could make. And many of these may only be used a handful of times as well. So much like I described with those prepare points, we maintain a hit count inside of the generic dispatcher I described. So we start still using that generic dispatcher for all of these transitions. We don't have to compile any code before your application can run. And then anytime we see that a transition is happening a lot, like you've got this one piece of code that lives in the interpreter and you call it a lot, we see that hit count has hit a threshold, and we now compile a dedicated helper for it. And now we exploit that thing I mentioned before, the WebAssembly function pointer table. We're able to take a function pointer and change what it does. We can actually swap the code underneath the function pointer. So the function pointer table is a very unique thing built into WebAssembly. We mentioned before that there are safety concerns in WebAssembly. That's where those control flow constraints come from. Similarly, they put constraints on function pointers. There is a big table of all of your functions, and an individual function inside of that table might be implemented in JavaScript. It might be implemented in WebAssembly. It might even be implemented in the web browser. And some of those functions may not actually be available right when your application starts. A great example of that would be, let's say you're loading a DLL 30 seconds into your application run. That's not available right away. So the solution for all of this is they have a big table. Every function pointer is an index into that table. And at any point, you can load functions into that table. And anytime your WebAssembly code is calling an unknown function, performing an indirect call, whether it's a delegate or a function pointer or a virtual method, the WebAssembly runtime looks that pointer up in the table and goes, OK, I found this function. I found function number 5. Does the signature match? Like, does this actually expect 3 arguments? Because I've got 3 arguments. And then if everything matches, it then actually calls that function. We can modify this table anytime we want, which means, hey, we've got slow code here for calling function number 5. It's a delegate. We didn't compile any code for it up front. But now we've called it so many times, we want to generate special code for it. So the Jiterpreter will compile dedicated code for that, and we swap it into the table, and your application instantly gets faster. This table happens to be unique for each thread that hosts WebAssembly. So this is one of the complications that explains why, while we do have threading support in .NET 8, it's not officially available. We're still working on a lot of the rough edges and making sure everything is perfect. And this is one of the reasons why we've had to do that work. It's a very interesting platform with a lot of fun constraints and features like this. So finally, the results. On January 31st, we enabled the Jiterpreter, the first pass compiler, in the .NET Runtime repository. And then on March 10th, we enabled that second pass I described called the CFG on March 10th. The result of this is that present day, a lot of real code is 75% faster when you're using the interpreter. For slower cases that don't benefit as much, the gains are more like 25%. But we found that across our big suite of benchmarks, we have something like 10,000 benchmarks. We saw about 3,000 of those got significantly faster, and only around 100 of them got slower at all. So we've been very, very happy with the results of this. This only added a small amount of new code to the runtime as well, basically just the implementation of this JIT. It didn't add any new special failure cases as well. If something stops working in the Jiterpreter, it just shuts off and your application will keep working. So we've been really thrilled with how all of this has turned out. So at this point, I'll open it up for questions. I'm really excited to see what kind of results users are going to get from this technology when we finally put the final version of .NET 8 out into the wild. And I hope anyone who has been testing out previews or will test out the RCs will let us know if you hit any problems with it or you have ideas for how we can improve it.
Awesome. Yeah, those results looked amazing. This is very, very exciting. So yeah, I'll go through some of the questions that people have left. So one is, one commenter is wondering if there'd be any reason to disable the Jiterpreter on low-memory devices like phones. They mentioned like the jumping between like IL and TypeScript and C function pointers.
That's a fantastic question. So the Jiterpreter does use some additional memory, and we've in fact had to navigate some nuances of web browsers where in some cases they were using a lot of memory. So to solve this, we have a built-in memory limit where the Jiterpreter will only use a certain amount of memory. We set that to ensure that we're not going to cause your tab to crash by using 200 megabytes of memory for your traces. However, as you pointed out, some devices like phones have very low memory. In those cases, if you're getting crashes because you're running out of memory, you may want to disable the Jiterpreter. There is a MS build property you can set in your project files. I forget the name of it, but it's in the documentation. So if you encounter memory usage issues that appear to be due to the Jiterpreter, you can turn it off, and you can file an issue on the .NET Runtime repository to let us know that you've been hitting these issues, and we'll work with you to figure out whether there's something else we can do about it. But as a starting point, I would say you should leave it on. Historically, it doesn't use a lot of memory. It uses a pretty decent amount, but not more than your application does.
Awesome. Let's see. Oh, one sec. My machine is asking me to restart. Restart later. Okay, good.
Oh, no.
Yeah, so that was a close one. So yeah, there's another question. How's the relationship between the JS thread method, I'm guessing, and WASM multi-threading other than multiple tables?
Great question. So for threads in WebAssembly in the web browser, at least, the way this works is we use JavaScript web workers, which are the JavaScript equivalent of threads. So when you create a thread in C# or in C, that thread will claim one of the JavaScript threads that is available. And as you guessed, each one of those JavaScript threads has its own table. So when we create these function pointers, we need to create them in each of those threads and update the table. Right now, our solution for that is we do it on the fly when it's needed on each thread, which has its own kind of complications and difficulties.
Awesome. Another question, what documentation, blogs, and folders in .NET Runtime, etc., are available to explore this topic further?
So we may be publishing some more extensive documentation on the Jiterpreter, but there is a design overview document in the .NET Runtime repository. I will grab the URL for that really quickly so we can share that with the users. It's definitely something where we would be happy to explain more about what we've been doing here, depending on what the community wants to know and what kind of experiences the end users are having. But right now, we basically have the implementation, which is written in TypeScript that's meant to be understandable as possible. And then we have this design overview that is checked into the .NET Runtime repository.
Awesome. If the stream doesn't let you post a comment, feel free to just message the link to me and I can post it, by the way.
I put it in the stream chat there. Oh, I see. Here, I have to connect my YouTube account, so it's probably best if you put that link in there.
Yeah, sounds good. Yeah, if you send it to me, I can paste that.
All right.
So
over here.
So I see a question about Jiterpreter on server-side rendered components. The Jiterpreter wouldn't apply for server-side rendered components because they don't use WebAssembly, is I guess the short answer to that.
Correct. Basically, we already have a JIT on the server side. So server-side rendering already has the .NET Runtime's fantastic JIT and AOT compilers. This is basically filling in the gap for Blazor WebAssembly on the client.
I think the link should be posted in the chat now. So thank you. Let's see. We had some questions near the start that are higher level. So one is about the WASM runtime being mono-based. Like, is it still mono-based? And like how does that work, I guess?
Fantastic question. So as you saw, the mono development process merged with Core CLR. All that development now happens in the Core CLR repository in .NET Runtime. The way it works now is essentially mono is now a component of .NET, much like, say, RioJIT, the JIT compiler, or the garbage collector. These are all components of the .NET Runtime, and it's possible to use different components depending on your scenario. And for Blazor WebAssembly and for Uno and other targets, what we're doing is we're using Core CLR, and mono is inside of it, acting as the interpreter and the AOT compiler. So as a result, we don't have to backport new features to this. There are specific things that might need to be added to the interpreter to work or added to the AOT compiler. For example, static methods and interfaces, we had to add that to this when it was added to the .NET runtime. But for the most part, things like the base class library are exactly the same.
Got it. Makes sense. And I think that's about it from what I can tell. So nice. And then I did run across another, more of a comment. So yeah, preview 7 of .NET 8 is releasing today. So please, for all of you watching, it would be great if you could check that out and give us feedback on that. But yeah, I think that about wraps it up. So
I saw a question about threads. We don't have anything to announce there other than that it's in development. We will be hopefully getting it into some sort of preview in the future. At that point, we'll announce it. So if you're looking forward to testing threads, that will be the right time for you to test it, is when we announce we got it in a preview. I don't think we have a specific target date for that yet, but know that it's actively in development. I've been working on it locally, like making sure all of this works with threads.
And we have an appreciation comment. Really enjoyed the technical deep dive. Didn't have many of these since uni, so many years ago. So thanks to Katelyn, and please do them more often. So
yeah, glad to hear this talk was informative and people enjoyed it. I saw someone ask if there are limitations on size of the pointer table. That's actually a great question. There is a limitation on how big it is, and you actually have to size it in advance. It's difficult to resize it. So what we do is we basically reserve a set number of spaces for things like traces. And then we do that at startup. And as a result, we've got all of these fixed spaces that we have ready to go. This is actually why you may occasionally see weird problems with delegates and AOT, is because we have to pre-reserve that table.
Nice. Do you see any other questions that jump out, or?
So I see a question about garbage collection for WebAssembly. We've been looking into that spec. The WebAssembly garbage collection spec is designed for sort of a lowest common denominator. The garbage collector in runtimes like .NET and in Java tends to have features that are not going to be available in the spec. So right now we have nothing to promise there, but we're actively working with the WebAssembly spec teams and with the browser developers. So were we to take advantage of it, you might hear about it from us, say, in the .NET 9 development cycle, but you shouldn't expect anything like that in 8. As far as WASM components in the browser go, I see there's a question about that. We have nothing planned in terms of supporting things like the WASM component model or any of that sort of stuff. That is also something that we'll be paying attention to as it occurs in the future. Currently, it's not even on our radar at all, so I wouldn't expect it. But if you see cases where you would like us to support it so that you can use it in your applications, please do let us know via filing an issue on .NET Runtime and giving us sort of an explanation of like, hey, here's this feature I'd like to see. Here's why I need it for my application.
Great. So
Okay,
I think
looks like that's it.
Yeah. Awesome. So yeah, thank you again, Katelyn, for doing this. I think a lot of people, it looks like a lot of people really enjoyed it. And I guess this is a sign that we should, keep doing these technical deep dives in the future. So yeah, I guess I'll go ahead and run the closing sequence. So thanks for watching, everyone, and we will see you next month.